So we're in the final stages. We're about to prove, so recall what we did. In the interest of time, will you allow me to be a little bit impressionistic and leave some details to your imagination? Okay, so what did we do last time? Where did we stop? Right, we computed the logarithmic derivative of the zeta function. We saw that this was a Dirichlet series, which if we pull out a minus sign, goes like this. It's log of 2 over 2 to the s, plus log of 3 over 3 to the s, plus log of 2 again over 4 to the s, plus log of 5 over 5 to the s, plus log of 7 over 7 to the s, and so on, which of course is a long way of writing. You sum over all the integers, and the coefficient you put in front of them is the von Mangold function, which if n is a prime power, then you put log of that prime, and otherwise you put 0. Okay, so that's the coefficient. 4 is the prime power. So the next coefficient would be log 2 over log 8 over 8 to the s, and log 3 over 9 to the s, and so on. That's the function that we were interested in. We got there from taking, we got a functional equation and analytic intuition for zeta by taking the any nice function. Let's say f is even, smooth, and nice. I guess nice could have gone into smooth. So this is the values. This will match 1 over t times the sum over m f hat of m over t, except that we've taken out the values at 0 and we've divided by 2. So this side will have an extra 1 over 2 t f hat of 0. And I moved to this side. I'm just reminding you what we did last time, half of f of 0. That's just Poisson summation. So Poisson summation told us this. We took Mellin transforms of both sides. So the integral from 0 to infinity, a sum of the positive numbers of this. This is a theta function. T is a positive real number. So in the t variable, we took a Mellin transform and we evaluated it. So this is okay. This evaluation was okay if the real part of s was bigger than 1. With good reason. There's a pole at s equals 1. But if the real part of s is bigger than 1, then this converges absolutely. We interchange summations. Out came the Mellin transform of f times the zeta function. I'm reminding you what we did last time. Then we kept, this has very nice decay properties at infinity. We kept that integral. But from 0 to 1, we plugged in this side times t to the s dt over t, and we made a change of variables, which came out to an integral from 1 to infinity. There's this factor, n bigger than 1, f of nt all times t to the s. And then there's this factor, which is this, which comes out to a sum over the positive integers f hat of mt. Once we make a change of variables, t goes to 1 over t. This becomes a t, this becomes a minus s, so we get a factor of t to the 1 minus s. And that's all integrated dt over t. And then these last bits we can evaluate explicitly, which come out to something like f hat of 0 over 2 times 1 minus s minus f of 0 over 2s. Does that ring a bell? This is what we did last time. We observed that this is entire. This, well, is also meromorphically continued. So that's the continuation of zeta. So this is continuation. This is the continuation. As long, this whole thing, as long as f has a continuation, and then we made a special choice. We chose f, not f tilde, f of x to be the Gaussian, in which case the Mellin transform comes out to, what is it? It's like a half pi to the minus s over 2 gamma of s over 2. These are all calculations from last time. I think I got that right. Yeah, at least that's what's in my notes. And so what does that mean? That means zeta of s, if I divide by f tilde, is a half pi to the minus s over 2. Of course, I could have put that in the denominator. Gamma of s over 2 times this integral. And this is an integral from 1 to infinity. We put in the theta function, which is its own Fourier transform. It's even. Its own Fourier transform. So this is times an integral, so a sum n bigger than 1, e to the minus pi n squared t squared, because that's what this evaluates to, times these contribute the same thing. So there's just the t to the s plus t to the 1 minus s, dt over t. And there are these extra factors. F hat is 1 and f is 1. F at 0 is 1. So we get 1 over 2 times 1 minus s minus 1 over 2s. Okay? This is the Riemann zeta function. That's why it has Riemann's name on it. Riemann zeta function. Okay? Not because it looks like a Dirichlet series, but because this is now meromorphically continued to the entire complex plane. We saw that we care, if we want access to primes, we get the primes through the Euler product formula by taking logarithmic derivatives. So we care where the zeros and poles of this thing are. What's important, we need to know something about zeros and poles of zeta. So zeros, well, we know from the Euler product formula, Euler product implies zeta is not 0 on where the Euler product converges absolutely. So far we know if we're bigger than 1, here's the vertical line 1, over here there's no zeros. Zeta does not vanish, right? It's a convergent product and none of the terms are 0. So the product is non-zero. So far, so good? This is all review. Now, we need to know, do we pick up zeros by dividing by gamma? So here's a formula that I'll leave as an exercise. It's a pleasant exercise. Not to be handed in, but just for fun, or read it in the book. If you take gamma of s and multiply it by gamma of 1 minus s. Now, you have to do this in the region where both of these are defined by the Mellin transform. So that's when the real part of s, or just do it when s is between 0 and 1. That's kind of the easiest thing. You verify this formula on an interval. Well, an interval contains a limit point, and then it's true for all complex s. This comes out to pi over sine of pi s. So it's a very pleasant exercise. You open both integrals, you interchange orders, and you can figure this out, okay? And if it's true in this range, means it's true for all s. Now, where does the sine function have poles? Not zeros, but poles, the sine function. Not 1 over the sine function, the sine function. No poles. This is entire, which means 1 over it has no zeros. Now, it might be that the gamma function has zeros and the poles of gamma at 1 minus s cancel them. So where are the poles of this? This has poles at simple poles at s equals, you guys remember? We analytically continued strip by strip. We started out real part of s bigger than 0. So we get poles at 0, -1, -2, -3, and so on. This has simple poles at s equals also, or 1 minus s rather, 1 minus s equals 0, -1, -2, -3, and so on. But wait a second. if 1 minus s is equal to this, then s, when 1 minus s is 0, that's when s is 1. This thing is equivalent to s being 1, and then 2, and then 3, and then 4, and so on. So these poles give us 0 and the negative integers. These poles give us the positive integers, and that's all the poles, because that's exactly where sign vanishes. This is where sine, so 1 over sine of pi s has poles for s in z, which are perfectly complemented by the gammas. And so what that means is the gamma function never vanishes, never ever vanishes. If this vanished, either this would have to have a pole, which doesn't happen because 1 over sine sine is entire. So 1 over sine doesn't, sine would have to have a pole so that 1 over sine would have a 0. It would either have to vanish, or it would have to, either this side would have to vanish, or this side would have to have a pole where this side vanishes. But the poles are simple poles and perfectly match the polar behavior on the other side. Okay, so we get that gamma is not equal to 0. Now let's stare at this formula. Right, and the other thing that we notice, if we had this on the other side, forget about the 1/2, pi to the minus s over 2 gamma of s over 2 zeta of s, this thing is completely invariant under s goes to 1 minus s. There's an invariance under s goes to 1 minus s. Not when you put this factor in, just to here. Okay, zeta by itself does not have this functional equation, but zeta times this local factor at infinity does, which means that this is equal to pi to the negative 1 minus s over 2 gamma of 1 minus s over 2 zeta of s. Okay, so this thing, let's figure this out. Let's see. So this thing, let me make a little room here. This thing has poles at s equals 0 and 1. But this thing contributes zeros. This part has zeros because gamma has poles, gives zeros at s over 2 equals 0, negative 1, negative 2, and so on. You see that? And so, which of course is the same as s equals 0, negative 2, negative 4, negative 6. So the 0, the pole of gamma at 0 cancels the pole of 1 over s at 0. And so actually the zeta function is regular at 0. Okay, so at 0, zeta is regular. In fact, zeta of 0, it turns out, is negative 1/2. At 1, we of course have a pole. That's this. This gives us a pole. And then the fact that gamma blows up at the negative even integers means that zeta has zeros at the negative even integers. So this is negative 2, negative 4, and so on, negative 6. So these are the zeros. Okay? Does that make sense? And we can really see that. Let me try to show you just for your information. Okay, you can see this. So let's make this nice and big. Let's plot zeta of s as s goes from minus 10 to 10, say. So what happens? So this is just the function zeta as a real function. So on the real line, let's see, let's make the plot range minus 10 to 10 in the x variable and minus 1 to 1.5, maybe 2. the y variable. Okay, so I don't know if you can see. So there's this pole at s equals 1. That's right here. The pole at s equals 1 shoots off to infinity. Here at gamma of 2, zeta of 2 is pi squared over 6. So right there at 2 is pi squared over 6. At 1, we have a pole. It's a simple pole. So what it means is it blows up this way. It's an order, it's like 1 over x, right? It's like 1 over s. It's like 1 over 1 minus s. So it goes to positive infinity from the left and negative infinity from the right. Here's, I said zeta of 0 is negative 1/2. Here we get the 2 and we get our first 0. Let's zoom in on that. So now I've zoomed way in the y-axis so that we can see. We get a 0 at negative 2, a 0 at negative 4, a 0 at negative 6, a 0 at negative 8, and so on. Okay? So that's the zeta function along the real line. Along the real line in this, this extended zeta function, in the extended form. Okay. Back to our here. Okay. You guys can see this? Any questions so far? So far, so good? Now, what do we know about zeros over here? Well, once we have this, this does not equal 0. So let's say real part of s is less than 0. Okay? So this is never 0. It's an exponential, e to the minus s over 2 log pi. This, we already know, is never 0. So the question is, where is this 0? And let's look over here. This, again, is never 0. And this, what do we know about this? Oh, that's a real, oh, God. Nobody's stopping me? Real part, zeta of 1 minus s. 1 minus s has real part bigger than, real part of 1 minus s is bigger than 1. So this doesn't vanish. So in this entire range, zeta is also not 0, just by the functional equation, just by looking at the functional equation and gamma. So the only possible zeros are in, so definition, the critical strip. Critical strip is the set of S, so that the real part of S is between 0 and 1. And any zeros in here are called, so these are called the trivial zeros. These are the trivial zeros. And these, if there are any, and there are the non-trivial zeros. Okay? Let's see. We did one more thing last time, if I recall. So maybe we didn't get to it, this zeros discussion, but so far so good? Any questions? Okay. So then what we did, and of course the center of this critical strip is the critical line. Critical line is the line S equals 1/2 plus IT. IT is real. Okay, so down the middle, this is 1/2. The line of symmetry, right? This S goes to 1 minus S symmetry, which, by the way, the gamma function also has, as you can see. This is invariant under S goes to 1 minus S. Let me just point out. Just because of the way sign works. But this side is invariant just because it's obvious, because it's symmetric in S, replacing S by 1 minus S. Okay, so the next thing we did was we computed the explicit formula. Explicit formula. The explicit formula was we took negative zeta prime over zeta. We multiplied by the Mellin transform of some nice function. Let's say this is entire. We multiplied by x to the s, and we took the inverse, well, that is the inverse Mellin transform. Almost. This should be an x to the minus s, but it's more convenient for all kinds of reasons to put an x to the s there. What we computed last time, if you recall, was if you open up, so this is put in the definition in the range of absolute convergence. Put in the definition, or not the definition, but the series expansion, and you get a sum over the integers von Mangold times the original function phi at n over x. You guys remember that? And then the other thing we did is we pulled contours, or we pull contours from the vertical line 2 back all the way to infinity. I mean, back forever. And we picked up, this is entire, this is entire. We pick up poles and we pick up residues from the zeros and poles of zeta, which are the poles of the logarithmic derivative of zeta. So there's a contribution at 1. So this is phi tilde at 1, x to the 1. And again, the beautiful thing about the logarithmic derivative is the residue is always 1 or -1, depending on if you have a pole or a 0. And because we have a negative sign in front, it flips which is which. So the pole at 1 gives us a positive contribution of phi of 1, x to the 1. And then we get a negative contribution for all of the zeros of phi of rho x to the rho. Now, some of these zeros are the trivial zeros, and the rest of the zeros will be these non-trivial zeros inside the critical strip. This is an exact formula, and I want to show you this formula in the case. So take phi is equal to the indicator function. We've seen this function many times now. The indicator function of 0, 1. Do you guys remember what the Mellin transform is? We have a Mellin transform pair.
One over s?
Beautiful, beautiful, 1 over s. So this is not entire. This is not entire, not entire. So when we do this contour pull, so let's write down the formula. We're going to get one extra contribution. So here we would get, of course, it takes a lot of work to make this formula work for a function which you can't apply this to. But never mind, let's pretend, you'll see that it works anyway, and this is what Riemann proved. So this is the indicator function that n over x is less than 1, which is the same thing as saying n is less than x, right? This was our step function. I think we called it psi or something, the Chebyshev function. So this is the function, this is this step function that jumps by log as we go along. Right? It's like the prime counting function, except bumped up by log, and also the prime powers are there, but it's basically the step counting function. How about on this side? We get an x to the 1 times 1 over 1 minus a sum over all the zeros of x to the 0 times 1 over the 0. And there's one more pole. There's a pole at s equals 0. That we have to pick up. Let's make that a little bit more clear. There's a pole at s equals 0 that we have to pick up that contributes zeta prime. So there's a factor of negative zeta prime over zeta at 0 times x to the 0. This, it turns out, comes out to log of 2 pi. I'll leave that as an exercise. And so let's see this formula. So I claim that this really is an identity, and I want to show you this identity. Okay, so can you remember this? As I switch to Mathematica? You'll have to remind me what it is since I'm not writing it down. Here's Mathematica. Okay, we can see this again. So let's see, do we have the von Mangold function? I think it's called Mangold. Mangold lambda of 7, of 8, of 9, whatever, log 3, good. And now I want to plot the sum of the von Mangold function as n goes from 1 to x. And I want to plot that as x goes from, let's say, 2 to 20 or something. All right, there's our step function. So again, it jumps by at 2. Okay, let's make it from 1 to 20. I don't know, 1.2 to 20. I don't want to deal with, you'll see in a second why I don't want to deal with 1. Okay, so so it starts out at 0. At 2, it jumps by log 2. Then it jumps by log 3. Then it jumps by log 2 again. Then it jumps by log 5. Then it does nothing. Okay, this is familiar. And now let's compare that to, what was that first term? The first term, whoops, here. The first term was just x. X to the 1 over 1. It's just x. There's that line. Remember, we have this minus log of 2 pi factor. Ah, that's better. That minus log of 2 pi, which is coming from the residue of 1 over s at 0. Did I get that right? I think I got that right. Let's see. Zeta prime of 0 divided by zeta of 0 is log of 2 pi. Good. Okay, so that's what this term is. I'll leave it to you how to work this out. It's not hard. Great. So let's look at the difference. Remember, we saw that there was this difference. So let's look at the difference of these two things. And we get this crazy function. Now, I claim, or Riemann claims, that when you start adding, so let's see, the kth contribution, let's say of k and the kth 0 and x, is to take zeta 0, the kth zeta 0. So zeta 0 of 1 has real part 1/2 and has imaginary part 14i. Okay, so it's at 1/2 plus I times 14. And the next one is at 1/2 plus 21i. And the next one is at 1/2 plus 25i, and so on. Okay, does that kind of make sense? So these are the zeros of the zeta function inside the critical line. And of course, they're all on the critical strip as far as we can tell. Otherwise, the Riemann hypothesis wouldn't be much of a hypothesis. So far, so good? You see what I'm doing? So what I'm going to do is take x to the row divided by rho. That's not a very good, that's not going to converge. I have to take them in conjugate pairs. So if there's a 0 at 1/2 plus 14i, there's also a 0 at 1/2 minus 14i. So that is plus x to the 1 minus zeta 0 divided by 1 minus zeta 0. Okay, let's see. Let's plot the kth contribution at 1x. So this is the first contribution as x goes from 1 to 20. There you are. What is this? The real part, let's look at this. This is x to the 1/2 is common to both of these. If I divide by x to the 1/2, x to the 0.5, it's just a sign. It's just a sign with an extra log, because that's exactly what this is. It's x to the, it's x, which is e to the log of x. It's x to the it, x to the 14i, and then plus x to the minus 14i. It's just a logarithmic sine function. Okay? Now check this out. Let's look at what happens if we look at this kth contribution. Let's look at the first contribution of x. That doesn't look, oh, it's because I didn't put parentheses around this subtraction. Well, that's a little better. That's just the first contribution. So that's the 1, 0 at 14i. You see what I'm doing? And here's the 0 at 21i. And here's the 0, let's see. This thing minus this thing will be negative of these zeros, the negative of these zeros. That's a little better. Let's take a whole sum of these. So those are the first two contributions. Let's take negative the sum of the kth contributions as k goes from, how many zeros should we take? 10 zeros? 5 zeros? Let's try 10. You see the green? Let's get rid of this. You see the now it's yellow again? See this yellow curve? That's with 10 zeros. All right, I don't know how long this is going to take. I'm trying to convince you of this formula. This is Fourier analysis on the primes, using the zeta zeros as the harmonics. The zeta zeros are the harmonics that tell you what the primes are. Okay, so here it is with 30 zeros. And the theorem, Riemann's explicit formula, is exactly what we see here. Any questions before I leave Mathematica? Anything else you want to see on here? Are you convinced? Okay. Okay, you can see this again. So that's exactly what we did. We looked at this. We looked at this difference. We looked at the sum n up to x von Mangold minus x minus, I guess, minus log of 2 pi. And that function is basically a squiggle function, right? Because this thing is a step function. This is a linear function. It's just some random squiggle function. And we compared that to negative the sum over the zeros of x to the 0 over 0 grouped. So you group rho and 1 minus rho together. So all of these zeros at a half plus 14i and a half minus 14i, if you look at what the term is, we have a half x to the half plus 14i over a half plus 14i plus x to the a half minus 14i over a half plus 14i. There's an x to the half that pulls out. And what's left is like a sine of a log. And at times a constant. That's what we were seeing, that squiggly, these beautiful squiggles. That's this squiggly sine function like that. And when you add all of those squiggly sine functions over all of the zeta zeros, you exactly recover. It's just like Fourier analysis. You're decomposing this wave by these things. And each of them has growth rate x to the 1/2, because 1/2 is the real part of all the zeros. Then there are the trivial zeros. So these zeros at -2, -4, you can handle these explicitly. I'll leave it to you. Let me just point out that the non-trivial zeros contribute x to the -2 over -2 plus x to the -4 over -4 plus x to the -6 over -6, and so on. If you pull out a factor of a half, then what's left is log of 1 over 1 minus 1 over x squared. I'll let you work this out. It's a simple exercise in power series.
You mean the trivial zeros, right?
The trivial zeros, thank you. The trivial zeros contribute this, and so some people will pull this out and leave only the non-trivial zeros. Okay, that was all review, and now I want to get to the new stuff. That was all review. Right, there was one more thing. Let me leave this as an exercise, although I think we discussed this last time. So first of all, the sum of the von Mangold function is the sum over all the primes up to x. I don't know why I put, it doesn't really matter, but I prefer not to put the equal sign, plus an error of size x to the 1/2, like x to the half log x or something. So in other words, the prime powers that contribute to this contribute almost nothing to the sum, asymptotically. They're a rounding error. And another exercise, so this is exercise 1. Another exercise is that this function, the sum over the primes log p, is asymptotic to x if and only if, but all we care about is the one direction, the prime counting function, which is the sum over primes less than x of 1 instead of log p, is asymptotic to x over log x plus little o of x over log x. Okay, and of course you should do much better here. You should really do the logarithmic integral. But this is a very standard, easy exercise. Let me give you a hint. Is if you do use, I mean, it's just summation by parts, partial summation. And if you do this as a Stieltjes integral, pi of x is, I guess I'm doing the exercise for you, which I didn't want to. So let's call this function, did we call it something psi already? I think not. Let's call this function psi, although really this one's called psi, doesn't matter. We'll call this psi. D psi of t, psi is a bump function. So its d is a Dirac delta only at the primes, and it jumps up by log t if t is a prime. And so if I divide by log t, now it jumps up by 1 every time it hits a prime, which is exactly what this function does. It jumps up by 1 every time it hits a prime. So if you're happy with partial summation, the classical way, go ahead and do it. If you're happy with the Stieltjes way, then you just integrate by parts and you get psi of x over log x plus a constant minus an integral from 2 to x of now psi of t, and the derivative of log, I guess, is negative 1 over log squared, a derivative of 1 over log rather, with a factor of t. Can you still see this? Ah. All right, I said I wouldn't do the exercise, and here I am doing it for you. Log squared of t. Okay, and this is small. This is x over log x by the assumption. I basically, okay, I'm sketching the exercise. So knowing that this thing grows exactly asymptotically like x means that you've proved the prime number theorem. So we need to know that this function grows asymptotically like x, has the same asymptotics. Does that make sense? So the last thing we need for the prime number theorem, which the classical formulation is like this, but really the prime number theorem should be that the sum of the Mann-Mangold function is x plus little o x. And the proof of this, so I'm going to give you a quick proof if I can. We need two things. We need, first of all, that the real parts of all the zeros are strictly less than 1. So again, here's our complex plane. Here's 1. We have a pole here. We have no zeros. Zeta doesn't vanish. This is the graph of zeta. Down here, we're regular. We have zeros at -2, -4, and so on, -6. Here is the critical strip where it's a mystery. I need to know that there are no other zeros. This vertical line 1, I need to know that there are no zeros on the line. If all of the zeros are inside the line, that's step 1, to show that there are no zeros. So zeta, i.e. zeta of 1 plus it, never vanishes. And then the second thing we need to do is conclude from that the sum of the von Mangold function is asymptotic to x. Let's just say is asymptotic to x. This implication is already in Riemann's, he wrote one paper on the zeta function, one. Everything that we're doing is this one paper. This is Riemann's 1859 manuscript. This last step is what was finished finally in 1896, independently by Jacques Hadamard and Charles-Jean de la Vallée-Poussin. Same year. By the way, this is a curious fact. Hadamard was born in 1865 and died in 1963. De la Vallée-Poussin was born in 1866 and died in 1962. There's some duality between Hadamard and de la Vallée-Poussin. They're like born and dead in the same year. They proved their most spectacular result in the same year, and it's the same result. But anyway, I will give you a sketch of a proof of one. So their proof uses some crazy trig trick. This proof uses a trig trick, I would say, because it's not something robust. What is it? It's like 3 plus 4 cosine theta plus cosine of 2 theta is always non-negative. And the reason it's always non-negative is because it's a square. It's 2 times 1 plus cosine theta squared. This is something very special, and it did not generalize to any other kinds of L functions. Well, to Dirichlet L functions, but no higher rank L functions, higher degree L functions. But the proof that I want to sketch for you, we're going to take a break, but the proof that I want to sketch for you is from 1994. Brilliant idea of, this is a appendix by Goldfeld, Hofstein, and Riemann to a paper of Hofstein, Lockhart, Annals paper, which makes this trick into something robust. So I want to give you the robust version just so that you will have seen it. So we'll do that the zeta function doesn't vanish, and then we'll show Riemann's argument for how to get from the non-vanishing of the zeta function on the one line to a asymptotic formula for lambda. So far, so good. I know we're racing. This is my last chance to tell you something that I think is important and interesting. So we're going a little faster than usual, but I think it's okay. Let's take 4 minutes. Okay, let's go. So I wanted to show you, oh wait, what are you seeing? You're seeing the notes, right? New share, here it is. Okay, you guys see this? This is Euler's 1749 paper, where he introduces two things, something that he calls the loon here, which is the zeta function, except with alternating signs. And then he introduces a function that he calls the sun, this hot sun. He apparently very recently tried to do some calculations of a solar eclipse or something. And so this function doesn't make any sense to him because it blows up, except he's able to, just by formally pushing things around, he's able to recover an identity about the ratio of these two things coming out to a cosine. And he conjectures that the ratio of these two things, that this identity that he can see for some small values of n always holds. That's the functional equation in some baby form. Euler only saw it on the integers, one could argue, and but he saw that the relationship between the Euler is an absolute genius. Even though he didn't have really complex numbers the way we think of them now, he basically saw the functional equation. Okay, so he didn't have the analytic continuation and so on the way Riemann did. Here's what Riemann's paper actually looks like. So here it is, 1859. What is this? Euler product, summation 1 over n to the s. 1 over 1 minus 1 over primes to the s. Okay. Here he is taking a Gaussian and taking its Mellin transform. He's working out the Mellin x to the s over 2, dx over x, e to the minus pi n squared x. And that comes out to a gamma. This is how he writes gamma of s over 2, pi to the minus s over 2. And then there's an n to the s that comes out. So he takes the theta function, which he's calling psi, a sum from 1 to infinity of a Gaussian. He takes the Mellin transform of that and sees that that is a gamma function times the zeta function. You see this? You see how modern this is? You can just read it. he breaks the sum as an integral from 1 to infinity and an integral from 0 to 1, applies the functional equation, and gets the analytic continuation. And then he pulls contours. Here he is taking the logarithmic derivative of the zeta function, and over some a minus I infinity to a plus I infinity, 1 over 2 pi I, pulls contours. So he's doing things slightly differently from the presentation I'm giving, but it's so close. It's so close. It's very modern. All right, here are the first few zeros. We saw this 0, a half plus I times 14 and so on. And by the way, if you look at the zeta function up the half line, so it starts out, remember, zeta of a half is, I guess sorry, did I say zeta of a half? Zeta of a half, not zeta of 0. Zeta of 0 is negative a half. Zeta of a half is just some number, but it's some negative number, right? Because the zeta function blows up at 1 and then is negative until it gets to 2. Negative 2 is the first time it crosses 0. So it's negative. And then it goes into the complex plane and it starts doing these little circles. So when we go from 0 to 10 in t, we have not hit the first 0. When we go out to 20, now at 14, boom, that's a half plus 14i. And then we keep circling. And we're about to hit a half plus 21i will be the next 0. So half plus 21i and so on. So we start circling like this and just hitting the zeros little by little up the 1/2 line. You see what I'm showing you? Does that make sense? Here it is out to 40 and 50 and so on, and 60. So we're getting more and more zeros. It keeps circling around and popping through the origin and giving us zeros. These are the zeros of the zeta function. If you instead of take the real part of s equals a half, if you go up the critical line, not the critical line, but inside the critical strip at 3/5 plus it, I just chose some random number. Well, 3/5 again starts at some negative real number, and then the function is continuous. So it's going to do some similar, it's going to have similar behavior. Here it is out to 10 or out to 100. You see it's doing these loop-de-loops. Notice it has never hit 0. It'll get arbitrarily close to 0, but it'll never hit 0. So here it is out to 200 and so on. Okay, so it's going to hit, it's going to be dense. It's just not going to actually hit the value 0, or so we hope and dream. Okay, weird, wild stuff. That's the Riemann hypothesis. We already saw this. We already saw this. So we take x plus this constant plus the trivial zeros, and that's this fundamental. And then we saw how to add these things on. Okay, I just wanted to show you that. Let's go back to work. Okay, any questions on that? Some fun pictures for you guys to play with. Okay, here is the argument in Goldfeld-Hofstein-Lehmann. Look, it's not that far from what's here, but it's rather slick. So I'm going to cook up a function. Before I cook it up, let me let's come in here. So remember, we're trying to prove that the zeta function doesn't vanish. Here's what I'm going to do. Remember, zeta of s is a product over the primes 1 minus p to the s inverse, and log of zeta is a sum over the primes of negative log of 1 minus something, which has a series expansion, which is a sum over k, 1 over k p to the ks. This is negative log of 1 minus 1 over p to the s. So far, so good. This is all if real part of s is bigger than 1. So here's what I'm going to do. I'm going to make a really crazy function. I'm going to make this function f of s. It's going to use some zetas. Now I want to think of s as being a real number. S is real and bigger than 1. And I'm going to fix t. So I'm thinking of, really maybe I should be calling this sigma, but too late, I'm calling it s. S plus it, s minus it, and 2it, and minus 2it. And then we're going to put some powers on these things, as you'll see in a second. Okay, so far so good. I've just made this big, massive product of zeta things. In fact, the powers I will want, you'll see why I will want these powers in a minute, but I'm going to do that. Yeah, that's good. That will work. So what is this? This is, S is a real positive number. This is just zeta cubed of S. What is this? Isn't this just the norm of zeta of S plus IT to the fourth? Right? This is the complex conjugate. So zeta times zeta bar is norm zeta squared, and there's two of them. So there's norm zeta to the fourth. And how about this? Yeah, this is norm zeta of S plus 2IT squared. So whatever this is, remember real part of S is bigger than 1. Zeta is positive, this is positive, this is positive, this is a non-negative thing. But I want it to be more than non-negative. I actually want to show that this is always at least 1. And the way to show that something's at least 1 is to show that its logarithm is at least 0. So let's look at its logarithm. Look at log ft of s. The beauty about multiplying things and taking logs is that you get to add things instead of multiplying. So this is 3 times log of zeta s. I know what log of zeta s is. It's a sum over the primes, the sum over k bigger than 1, 1 over k p to the ks. And there's a 3 there. You guys see that? How about here? When I do the same thing, instead of s, I have s plus it. But again, I just get exactly the same formula. So there's a 1 over k p to the k s plus it. So let me take that plus it and make it a p to the minus k I t. And there's 2 of them. So there's a factor of 2 in front. Does everybody see how this term corresponds to this contribution? And the next term gives me a plus 2 p to the plus kit. And the next term gives me a p to the 2 kit. And the last term gives me a p to the minus 2 kit. Does everybody buy that? And here is the miracle, which is the analog of this Hadamard-Delvalle-Poisson idea, is to make something a square. The reason you know something is positive, the easiest way to tell something is positive is that it's a square. Squares of real numbers are positive. Let's look at 1 plus p to the it plus p to the minus it, norm squared. Norm squared, of course, I mean this times its conjugate. But actually it's already real. So it's just the square. Okay, so I get 1. I get the square of this, p to the 2it. I get the square of this, p to the minus 2it. And then I get cross terms. The cross terms are 2 of these, 2p to the it, 2p to the minus it. That's this cross term. And the last cross term is this. Yeah. So this whole thing is actually, and that's all, instead of it, it's to the kit. This whole thing is actually 1 plus p to the kit plus p to the minus kit squared. and S is a real number, and these are all positive numbers, and these are all apparently positive numbers. And so this whole sum is apparently positive. Which means that F itself remains at least 1. This is true for all. This is for all S greater than 1 and for all T. Can you smell the magic? It's about to happen. So what? Suppose zeta of 1 plus I capital T equals 0. Suppose there is a 0 at height T. Okay, so here's the zeta function. Here's 1. Here's some magical height T. And oh my goodness, we have a 0 in the critical. This would be awful. This would actually ruin the prime number theorem, because there would be a term that goes x to the 1 plus IT. It would fluctuate of size x to the 1. The asymptotic formula would not be x to the 1. It would genuinely contribute fluctuating terms to the prime number theorem. It would ruin the distribution of the primes as we understand them. Suppose this happens. So as S goes to 1 from the right, zeta of S plus I big T goes to 0. Okay? Now look at this formula. That would imply zeta cubed of S. Now this has a pole of order. This is a pole. Okay, let me write it first. Zeta of S plus I big T for this hypothetical value, I big T to the 4th, and then a zeta of S plus 2IT squared. This has a pole of order what? What happens to zeta of 1 over zeta of S at 1 as S goes to 1? Yeah, pole. It's a pole of order 1. When we cube it, it's a pole of order 3. So this looks like 1 over S cubed. Well, 1 over S minus 1 cubed. This has a 0. Of what order? You see that? This is a 0 of order 4. If you're analytic and you vanish, then you vanish polynomially. And so when you raise it to the 4th power, it vanishes to order 4. And this is regular. This is regular. It might vanish, it might not, doesn't matter. A 0 of order 4 times a pole of order 3 means that this thing goes to, yeah, awesome. Except, it's always at least 1. Contradiction. And so with a little bit more work, so that's basically the argument. That's Hadamard Factorization. With a little bit more work, I'll leave this as a fact. Using Hadamard's infinite product formula, Hadamard's factorization, there was a reason we did that Hadamard factorization for. I mean, it's interesting in its own right. You remember this Weierstrass infinite product? And Hadamard tells you if you have a function of order 1, by the way, these things, the zeta function is of order 1. I didn't prove that for you. But when you use Hadamard's factorization, what you get out of exactly this kind of argument is something stronger than just non-vanishing on the real line. What you can get is that zeta prime over zeta of S, if S is sigma plus IT, sigma plus IT, is that this thing is bounded by a constant times log t for all S on the line that goes like this, all S on sigma, or all S in the region, sigma is greater than 1 minus some little constant over log t. Okay, I know this is a mouthful. Think of 1 over log t. The real part has to be within a constant over log t of 1. So that's this region. Okay, of course, away from the pole. There's a pole here. So for t bigger than 1. And for all S in this region. You have a bound. Not only does this thing not blow up, but it doesn't blow up, and it grows at worst like log t in the t variable. Okay, can you are you willing to accept this argument? So not only does we prove that it's non-zero, there's room here. There's room between 1 and 0, and so you can use that room to prove a zero-free region. Not only does it not vanish on this vertical line, but actually it doesn't vanish in this entire region. By the way, if you would like a Fields medal, prove that it doesn't vanish on a vertical strip, any vertical strip. So zeta of S not equal to 0 on sigma greater than 0.99 implies Fields medal. Okay, we do not know anything like that. The only regions we know are ones that get closer and closer to 1 the higher up you go. If we had such a region, what I'm about to do is pull contours to this region, to the region where we have bounds, and pick up the pole at S equals 1. If I could pull the contour all the way to a vertical strip, we would have a power savings in the prime number theorem. We would know that pi of x is the logarithmic integral of x plus big O of x to the 0.99 instead of x to the 1. What we currently know is, well, you'll see in a second, something much, much weaker than that. Okay? All right, so let's finally do, so this was step 1. I gave you a modern treatment of step 1. Let's go back to Riemann's treatment and prove this asymptotic formula once and for all. We'll do it in smooth form, and maybe I'll run out of time since I don't think I'll have time to unsmooth it. So finally, prime number theorem. Again, we start with our old friend von Mangold phi of n over x summed over all the integers n being equal to 1 over 2 pi I, exactly as you saw in Riemann's memoir, over some vertical line, doesn't matter what it is, to negative zeta prime over zeta, the Mellin transform of this test function, x to the s ds. Okay, now I'm going to pull contours. If I pull contours to this region, let's call this curve gamma. Let's call this curve gamma. So if I pull contours, so I pull contours, I pick up a residue, I pick up x to the 1 phi tilde of 1. Instead of pulling all the way and getting the explicit formula, I'm only pulling to gamma plus 1 over 2 pi I, an integral over the vertical line 2. I mean, it's the same thing. Sorry, not 2, not 2. The whole point is to make the curve gamma, zeta prime over zeta of s. That's supposed to be a phi tilde of s, x to the s ds. Okay, so far so good? Now, phi being a smooth function, phi tilde of s, remember, is the Mellin transform of a nice smooth function, t to the s dt over t. And if we take two derivatives, phi double prime of t, we've seen this already. Can you see this at all? Phi double prime t to the s plus 1 over s times s plus 1 dt. You remember that formula? I just did integration by parts twice. Anyway, all I want to say is that we have that phi t of s in this region is bounded by some constant over s squared. And we could keep integrating by parts if we wanted to, but this will be plenty. So let's estimate this. Let's estimate this. In absolute value, this thing is at most. I don't care about any constants. I have an integral over this region gamma. Let me redraw gamma again. Here's 1, here's the curve gamma. Gamma is the curve sigma is equal to 1 minus constant over log t. Okay, and I'm going to break it into two regions. An integral from 0 to t of all of this stuff, plus an integral from t to infinity of all of this stuff. Okay? When we're in this range, I apply the bound that I have on zeta prime over zeta, which is this log t bound. So I bound that by log t. I bound phi tilde by 1 over t squared. And I bound x to the s by x to the sigma. And sigma, on this entire region, the real part, is at most 1 minus constant over log big T. dt. Does everybody see that? So this, I'm bounding here, I'm bounding x to the s by x to the sigma, and sigma is the largest it gets is whatever it was at this height. Constant over log t, right? This is 1 minus, this is height. This is a real part, the real part here. The real part here is 1 minus constant over log t. So far, so good? In this large region, I again bound zeta prime over zeta by log. I again bound phi tilde by 1 over t squared. And now, well, the real part is getting closer and closer to 1. The best I can do here is say it's x to the 1 dt. T is a parameter to be chosen almost right now. I was going to say later, but now. So what do we get? Less than, I don't care about these constants. Okay, I have an integral 1 over t squared. Well, whatever this integral is, it converges. This integral, I can extend it out to infinity and it still converges. The only thing I'll get here is x to the 1 minus a constant over log t. You see that? Because I have log t over t squared. And I'm not worried about 0. This is really at 2 or something. There's some constant amount that you don't bother with. And what about this integral? I have an x to the 1 that I can't do anything about, but now I have a 1 over t squared starting from t. So that gives me a 1 over t, really times t to the epsilon, times log t or something, or t to the epsilon, but never mind. Forget about this. So far, so good. You're with me. We're almost there. This is almost it. This is almost the prime number theorem. So I want to make, so let's put it all together. What we have is a sum over n, von Mangold. This smooth form, I'm giving you the smooth form of the prime number theorem. Here there's a main term of x times phi tilde of 1, which is exactly what we want. We would have to unsmooth this phi. It's not cooperating. There we go. Plus an error, which depends on phi, of course. Well, when we do the unsmoothing, we'll have to handle that extra error. And then there's a factor of x to the 1 minus constant over log t plus x over t. If t is very large, we win here, but we lose here. If t is very small, we win here, but we lose here. So now we have to do some calculus. Where's the optimal choice of t? Optimal choice of t, here's a little trick they don't teach you in calculus class. Optimal choice of t is the one that makes these two equal. Maybe they do teach you this in calculus. You don't have to take derivatives, just set the two equal. Optimal choice of t is when x to the 1 minus constant over log t is equal to x over t. There's an x to the 1 here and here. We can forget those. Let's play with this a little bit. I'll move the t to the other side. I'll move the x to the constant over log t to this side. And the power of x to the 1 and x to the 1 cancel. So far, so good. let's take logs of both sides since I want to get to this exponent. So I have log of t is equal to constant over log t times log x. And we can move this to the other side. So log t is equal to, log t squared is equal to x log x, see constant log x, which means log t is the square root. And what does that give us for our final error term? Von Mangold, smooth form, smooth approximation to an indicator function is equal to x p tilde of 1 plus an error whose constants depend on phi and its derivatives, some Sobolev norm of phi, x over t, these two will be the same, so I only have to evaluate one of them, x over t, t is e to the square root of some constant log x. So this is x to the 1 minus square root constant log x. Now maybe you're not so familiar with these weird functions that arise all the time in analytic number theory. So let me show you how much savings we actually get here. So x to the 1 is the main term. What's this x to the minus root log? This is a horrible thing. So how does compare? So let's compare. Let's compare to x to the 0.99. Remember I told you this would be an incredible thing? X to the 0.99 is x to the 1 minus 0.01. And 0.01 does not go to 0. This does not go to 0. Whereas, sorry, this does not go to, minus infinity. This doesn't get worse and worse. Whereas this bound, this is a savings, right? You want to think of this as like x over, oh, sorry, not x. It's x times e to the minus constant log x. That's what I'm trying to say. Maybe that's why I'm getting confused looks from you. E to the root constant log x. So this would be x over x to the 0.01, right? So how do these two denominators compare? X to the 0.01 is e to the 0.01 log x. What goes to infinity faster, square root of log x or log x? Log x, right? Log x goes to infinity faster than square root. So that's why this is much better. Much better than that. But if all we could prove is a bound of like x over log squared x, which is the naive prime number theorem, this is the same thing as x over e to the log of this, which is 2 log x. This is why, you know the one about the drowning number theorist. Yeah, you all know it. Not all of you know it. The last words of a drowning number theorist, log. Yeah, okay. Number theorists have a lot of logs. So log x goes to infinity much slower. This is much worse. This is a much worse error because this log goes to infinity much slower than square root log. Okay, so there's all these in-between error terms, and this is the prime number theorem in smooth form, and I don't have time to show you how to unsmooth it, but maybe I'll figure out some other way to do that, just so that you know how to finish the argument. But in smooth form, that's the prime number theorem, and that's all I got. It's been a fun semester, guys.